Now we need to explain how the general circulation gets set up. As I had indicated in the beginning of the chapter, this book takes a kind of an approach that is all about energetics and not hack through the equations. So if you want a beautiful exposition of the equations and the fluxes needed to move energy northward, then Holton is the best book for that, in my opinion. I'm sure there are others. So we need to define a couple of things here, understand the concepts. Potential energy for a fluid system is one of them. We have either done zonal mean meridional sections, or we have assumed longitudinally uniform or symmetric flows so far. We haven't looked deeply into the longitudinal asymmetries, how things change from one location to another along a longitude. We've mostly done latitudinal variations. So when we look at potential energy, obviously it comes to the vertical distribution of mass. Remember the stability thing we did in the 4th chapter, where we had a ball sitting at the top of the hill and the bottom of the hill, and if you pushed the ball, they behave differently depending on where they were sitting, right? So that is related to the potential energy. But now we have to go into a fluid which has got a distribution of density in the vertical. So far we have taken vertical profiles of density and not worried about the horizontal variations in density. That turns out to be very critical for generating motion by releasing potential energy. We'll see what we mean by that. So if we take mass of a parcel, that is just rho dV, a parcel with a volume v, gz is obviously the height times gravitational acceleration, which gives us the potential energy. So if you hold something here and you release it, it's going to fall down because its potential energy is going to get converted into kinetic energy, right? So the potential energy in that case is just a simple expression, g. We pull it out because we are again neglecting its variations in height. Integral of g rho dv, z rho dv. It's just the mass. Because rho has a profile, we have to integrate it, and obviously the mass of the parcel is integral rho dv, and the potential energy is then just g times the mass times this average z, which in this case is the height of the center of mass, which determines its potential energy, where the z angular bracket is just integral of z rho dv divided by rho dv, where integral of rho dv, where integral of rho dv is of course the mass. So it's the distribution of mass divided by the mass, so that you find the height where the center of mass exists. We looked at potential energy and energetics before in a very special circumstance, where we took an incompressible fluid with the stable vertical profile in the z direction, remember, and we had not considered any horizontal variations of density. And we had done these simple calculations where we say we move rho 1 from z1 to z2, and we move down rho 2 to rho 1. The system is in hydrostatic balance and it's incompressible fluid, so the parcel doesn't do any work against the environment as it moves up or down. There are no pressure effects. It's only a temperature dependent density change, right? So the idea there was to see whether when we exchange these parcels, whether the system remains stable or unstable, and that we had derived an expression in terms of the density gradient, which then we converted to the temperature gradient, and we said if density decreases with altitude, then the system is stable to these sorts of exchanges. If the density increases with altitude, then the vertical displacement, adiabatic vertical displacements will create kinetic energy by releasing potential energy. Okay, so we had done the energetics this way, looking at this rho1 z1, rho2 z2, and then after they've been displaced up and down respectively, we wrote the energetic initial distribution as g times rho1 z1 plus rho2 z2, rho1 z1 plus rho2 z2, and we displaced them and created a final potential energy of g times rho1 z2, which has been moved here, and rho2 z1, which has been moved down. And density is only dependent on temperature, and the adiabatic displacement means the temperature has not changed for rho1 and also for rho2. They maintain their temperature from the original position. So delta PE in this case, the change in potential energy in this case, is PE final minus PE initial, which ends up giving us this expression, which is approximately related to d rho dz and z2 minus z1 squared. Okay, that's the change in potential energy. The question then is based on the density gradient, which can be written as rho2 minus rho1 or z2 minus z1, assuming a small enough displacement. The stability criteria was that if d rho dz is positive, then the parcel that's moved up will be positively buoyant, which means you move it up, it's still less buoyant than the surrounding, so it'll keep moving. Whereas if it is 0, d rho dz is 0 straight up, then you can displace it and nothing happens. If d rho dz is less than 0, as in our case, then it is negatively buoyant, right? So move it up, it's negatively buoyant, so it'll come back. So we express that in terms of temperature because rho is a function of temperature. You can write rho equals rho ref plus 1 minus alpha T2 minus T1 kind of equation, and the temperature gradient also can be related to the stability. The long story short, in a horizontally non-varying stable density profile, adiabatic displacements will only increase the potential energy and lock it up, or there will be no change, which means potential energy is not released in this situation. Okay, so we look at these distributions in the real world where we had seen the zonal mean meridional sections, and we kept saying that there is heavy air near the surface, light air near the surface, and stratification is locking up the potential energy. So the main question we are going after here is to generate general circulation. We need to release this potential energy, and we need to figure out under what circumstances this potential energy gets released. Obviously, we have to move from the incompressible fluid we have considered to a compressible fluid eventually if we want atmospheric general circulation, which is the topic of this chapter. And we have to figure out how the air masses have to move, air parcels have to move to release potential energy instead of locking it up or not allowing it to be changed. Okay, so stable stratification, potential energy is greater than 0, but it's not available, which means adiabatic displacements do not reduce the potential energy. So going to our expression of potential energy as g times mass times the height of the center of mass, adiabatic rearrangements of the air column has non-zero potential energy, but it is not available for conversion into kinetic energy. Okay, this is the message. If you remember, you'll be doing well. You can only do that if there are horizontal density gradients. So if there are no horizontal density gradients, then you cannot release that potential energy, same as in the example of the incompressible fluid that we just saw. So stable stratification requires non-zero horizontal gradients of density for PE to be converted to KE. Our entire business of thermal winds has relied on having horizontal gradients in temperature and the vertical shear of geostrophic and so on. And if air density is dependent on temperature, then obviously horizontal gradients of temperature are going to give us horizontal gradients in density. So at each location it can be a stable profile, but it has horizontal densities, density gradients. So we can convert PE into KE in the atmosphere by displacements of parcels of fluid, and we have to see what requirements or what constraints there are on these displacements to produce KE by releasing potential energy. That's the crux of the story.